Every kilogram of propellant ejected backward at high speed translates directly into forward momentum for the spacecraft. This conservation of momentum is the sole reason we can maneuver in the vacuum of space, where there is no air to push against. The change in velocity, or delta V, depends on two primary factors: the effective exhaust velocity of the engine and the natural logarithm of the ratio between initial and final mass. We define initial mass as the rocket plus all its fuel. Exhaust velocity represents engine efficiency. It is often expressed as specific impulse in seconds, which we convert to meters per second by multiplying by standard gravity. Higher exhaust velocity means more change in speed for every gram of fuel consumed. Mass ratio is the wet mass divided by the dry mass. As the rocket burns fuel, its total mass decreases, meaning the same amount of thrust produces increasing acceleration. This nonlinear relationship is why we use the natural logarithm in our calculations. Because the relationship is logarithmic, doubling your fuel does not double your final speed. To gain linear increases in delta V, you must increase your mass ratio exponentially. This mathematical reality creates a steep ceiling for single-stage vehicles trying to leave Earth. Dry mass isn't just the payload. It includes tanks, engines, and electronics. If 90% of your rocket is fuel, your mass ratio is 10. Engineering a structure that can hold that much fuel while weighing so little remains a premier challenge of aerospace. Staging bypasses the logarithmic limit by discarding empty tanks. By dropping dead weight, the rocket effectively resets its dry mass mid-flight. This allows the remaining fuel to accelerate a much smaller total mass, significantly increasing the total achievable delta V for the mission. To reach orbit, a vehicle needs approximately 9,700 meters per second of delta V. Accounting for gravity losses and atmospheric drag, the rocket equation shows why a modern rocket must be over 85% fuel by weight just to succeed. Deep space missions require even higher mass ratios or more efficient engines. Moving from Earth orbit to Mars adds another 4,000 meters per second to the requirement. Every extra kilogram of payload at the destination requires dozens of kilograms of fuel at launch. Planetary size dictates the difficulty of spaceflight. On a smaller world like the Moon, the required delta V is much lower, allowing for simple single-stage landers. On Earth, the deep gravity well makes the rocket equation an unforgiving master of mission design. The only way to truly break the cycle of massive fuel loads is to increase exhaust velocity. Nuclear thermal or electric propulsion systems offer exhaust velocities far beyond chemical limits, potentially transforming how we calculate the future of human expansion into the solar system.